So, what did you do last week? Any interesting things did you do? Nothing?
Sir, can I say?
Yes, yes. Anybody can say.
I bought the science encyclopedia and the space encyclopedia and all about the space research.
Very good. Super.
I have it near. I'll show after.
Fine. I used to read a lot of books when I was young, and I had the interest from my father, who is like who's very crazy about reading books. So every day he would used to spend around 2 to 3 hours reading lots of interesting things. Have you seen National Geography Discovery Channel? Right? Have you seen it?
Yes, sir. I will see that.
So there used to be a publication that comes as a monthly magazine. It is a National Geographic magazine that had a lot of pictures and a lot of cool
I
articles.
used to get you a lot when I was in India, sir.
Oh, okay. So all this time, when I was in my little ages, as I was older as you, I used to get it at least once in a month, and I would used to scan and find a lot of interesting things. I would read about uh, space. I would read about history. I would read about the Inca people in Peru. It is in South America. I used to read about Antarctica. Why is there always polar bears in only in Arctic, and why is there no polar bears in the South Antarctic? All this kind of silly questions I used to ask. My father would say, "You go and read this book, you will understand." So all these things I used to learn from that. I think I've waited longer, so I think maybe she is held up in another meeting. So probably we will wait for Divya ma'am next week. Probably she'll come by that time. Until then, we'll go continue our story. Okay, on to our story. We are today seeing about, what are we seeing?
Sir, a clue.
No, we were continuing the thing that we saw last week. That was into a small part of an atom. A part of an atom. What is a very
Neutron.
yeah, yes, you are going to see
Neutron star.
you are going to see a little more about the neutron star. So that's the special thing for today. So we'll continue. So as you all know, we have been exploring the universe using our friends. So 10 of our friends have been constantly traveling across the Milky Way galaxy and finding interesting things to do. So we saw the last week about what is the life cycle of a massive star, what is a neutron star, what is its interior, what is it made up of, and why is it more significant for the discovery of neutron stars. I also gave you a clue about, we are also going to see a little part of what is inside a neutron star. So that was in the last week's episode, what is a neutron star. So a quick recap. So we saw the directions from where we started. From Earth, we went to solar system. From solar system, we went all the way to the topmost of the Milky Way galaxy. And from there, we were able to observe all the universe. So from there, we were also understanding what is made up of sun. So sun is a very normal looking star, which is the size of a average life of 5 billion years. So all this life, so from a starting point of a nebulae, from a dust cloud of all things floating around, it had evolved into a sun-like star, and probably it will become a white dwarf some billion years from now, some 5 billion years from now. So this is the evolutionary point of a birth of a star. So over many billions of years, all this hydrogen and helium atom will fall into gravity, and it will become a round thing. So it becomes a protostar, and that protostar becomes another kind of house for all the other stars to grow, and it goes on forever. And then it lastly, at almost to the dying phase, it becomes a red giant. And then probably, if time permits, it will transform into a white dwarf. So these are the ways in which a normal star will evolve. So for a massive star, it can either go into a supernova explosion, and it can start again rebirth of its life. You know what is a life cycle, right? A life cycle.
Yes, sir.
So it starts from one thing, it transforms into something else. From a small worm, a butterfly is born, and from butterfly, a new worm is born, like that it keeps on going. So the cycle of life keeps on continuing. So like that, even a star has to go through life of birth and death for a very constant times. So this is how it has become using a supernova explosion. And finally, ultimately, if none of this opportunity happens, it can become a black hole. So one part of it, if that doesn't happen in a much bigger scale, it becomes very, very small, very, very tiny thing called a neutron star. So this neutron star is in the phase of a blue. It is very hot. It is very, very hot. And this neutron star is so densely packed. It is so dense. Even the biggest of the biggest suns, or the biggest of the biggest, what is the difference between a supernova and a nebulae? Okay, supernova is comes first. So I'll show you again. So this is a supernova. So it is an explosion which throws out all the lights. So it's a cloud of floating materials. So it can go in every direction. But a nebula is like, it's a condensed thing. So okay, I will give you another example. Okay, what do you like to drink? Do you like to drink Boost, Bonvita, chocolate drink? What do you like to drink?
Chocolate drink.
Okay. What about someone else? Nitin, what do you like? Chocolate? No chocolate? Okay. Lakshya, what do you like? Chocolate? Boost?
None of those, but I like normal milk.
Okay. Litika, what about you? You don't like anything? Okay. Fine. So take for example, now you are considering chocolate. Okay. With chocolate, what you can do it in two combinations. One, you can drink it directly or take it a bite from a wrapper or anything. That is one way. Another thing, you can join it with something else. Say like if you have a, what do you need for making a hot chocolate? How do you make hot chocolate?
I don't know, sir.
You need to have a pan. You need to pour it on a pan, and then it got to start boiling like a lava. Then it becomes a hot chocolate. Okay. What about if I want to make a frappe or a cold chocolate drink? How do I do that?
Freeze it.
Good. So there are two ways. So either you can heat it up or put it in a fridge. So now I'm going to mix two things. Okay. Take that chocolate. Okay. Make it as a chocolate kind of a very thick drink. After making it in a frying pan or any pan, and if you heat it for some time, it becomes a hot chocolate lava. This hot chocolate lava, you pour it inside a cold milk. What will happen?
Some gas-like thing will come.
And some gas like thing will come, obviously, but what will happen to the chocolate? Will it stay on the top of the surface or will it fall down?
It will mix.
Okay, it will mix, but will it mix very well or will it mix very normal? So it'll
Normal way, in a normal way.
okay. So now, instead of having a cold milk, I am heating the milk and now I am pouring the hot chocolate. What will happen? Hot milk, hot chocolate.
It will get mixed properly.
Yes. So that is the reason why supernova and nebula are different. See, supernova is like having a cold milk having all the elements. So it is floating in the space. It doesn't have a good mixability of all the temperatures. So it doesn't have all the elements filled with each other. But a nebula is like a collection of all the elements in one particular space. So it is hot and it is happening every time. So every second a nebula creates a new star. But for a supernova, it has already died. It has finished creating all the stars. So now it is almost in the phase of having so many neutron stars and black holes. So it is going to sit idly. So it is going to stay like this for like a cold milk. It is going to stay there. It is going to do this all the time. For all the time, it is going to take the time to make new star. So supernova is very slow, but nebula are very fast. So they make energy very quicker and quicker. So that is a difference between a nebula and a supernova. So this is all supernova. So it has created a lot of elements and it is throwing it out. So all these gases is now moving across the light years away from the center. So one part of it is also a black hole. So So supernova can also create black holes, and these black holes will suck all the light that is very close to it. So it can absorb every possible light that is very close to it. So also they can also make a neutron star. So we saw the temperatures, different types of temperatures. We saw the different types of sizes. So all these things are made sure that our sun is in the right time at the right age. So we are now in a place of creating more, cooking and more hydrogen atoms. So we are creating hydrogen atoms and we are burning them to create more energy. So that is the nuclear fission reaction. So 4 hydrogen atoms become 1 helium atom, and this keeps on going to create nuclear fusion reaction. So this makes energy and this makes light. So all the light that you see is coming out of our sun using this same principle. So this is our star's middle age. So it is almost in the age of 45 to 50 years old. So this is our sun's life cycle. So there is also an alternate cycle of a massive star, which is where the other two options come in. So either it can become a neutron star or a black hole. How does it become? So that is the way in which every sun's cousins are created. So the cousins I am talking about is different types of star systems that come in. So what is a constituents of a massive star? So there are non-burning hydrogen star, hydrogen fusion reaction, helium fusion reaction, carbon fusion reaction. All these things are happening inside a star, and this creates an ultimately very short compressed thing called neutron star. So this neutron star was first discovered by Jocelyn Bell. She's a very curious scientist who sat across the space and was observing all these things, and she found one thing. Okay. So the elements of a neutron star that you can find is constant of three things: an electron, a proton, and a neutron. So what is this combination of all these three things? What is this?
Sir, which sir?
Electron, proton, neutron. What is inside all these three things? Or,
It's in the atom.
correct. So it is in an atom. So atom is a very small thing. So from that, all the energy that is created is called by different things. So one is called pulsar, another is magnetar, and all this combined together to form a blue hazy kind of a marble. This marble is very dense, creates so much of things. Take note, only I'm going to tell this very one time, so because we are going to jump into the types of it and again. So there are three things in the atmosphere. Can you notice what are the three things that are there in the atmosphere of a neutron star? One is hydrogen, another is helium.
Hydrogen, helium, carbon.
Why is carbon so important?
Sir, is carbon an element in the carbon dioxide?
Yes, true. Carbon is an element in carbon dioxide. There is also one other reason.
When is the person from the NASA coming, sir?
We are waiting for her to come, Kanama. I'm expecting her to come, and I'm hoping that she will come by this time. I'm not sure. I've asked her to come by 6 before 6 so that we can introduce and we can have a lot of question and answer session. I don't know. Probably she's running little late in some other work. So we'll wait. We'll wait for some more time. Probably we'll wait for another 5-10 minutes. If she comes, we'll start her session. Okay. So why now coming to the question, why is carbon more important? What is the reason for having carbon?
Carbon burns out.
Carbon burns out. Yes, okay. Carbon is also something very fundamental for uh, life, correct? Why is carbon more important for life?
It's used to produce electrons.
Almost there. So carbon is like powerhouse. So most of the elements that you create come from the combination of carbon atoms. So when they die, when something dies, it gives out enough amount of electrons to make heavier elements. So iron, cobalt, magnesium, nickel, and all these things come from the next elements. Carbon is a very favorite thing because carbon can combine to form a long chain of compounds. It is called organic.
Carbon is also found in diamonds.
Everything starting from periodic table of 6 and above has a certain fundamental reason to create complex elements and complex compounds. So carbon is most important of it. So like that, when neutron star and a black hole combine together, there are many combinations in which they can work. So they can collide and create beautiful spectrum of light. They can create so much of combinational things. And there is also a time in which they will live. So they will live for a longer and longer periods of time, and possibly the neutron star that you are seeing right now is going to live for hundreds and hundreds and thousands of years. So they are mostly going to be immortal. So the nearest neutron star is probably very far, so you can't reach it by a normal play. And this is how it looks. So inside it is a very tightly packed thing. It doesn't come out very easily. So from the year 1054, they have been finding new supernovas, and they have been finding neutron stars very commonly from there. So this is what we saw in the last week. So in this week, I'm going to start with an important question. So what is this?
It's a pencil drawing.
Okay. And notice what he is drawing. What is he drawing? The one in the left.
He's drawing an image by drawing spirals and creating an image of a face.
Okay. So what is the color that he is using?
Only black.
Okay, only black. You know the reason why?
No, sir.
Any guess? Someone else? Can anyone guess?
Black can shade differently.
I'm asking about the element that is used for creating black. What element is needed for creating black?
Graphite.
Okay, you're almost there. Graphite is something that is a
Or
compound.
coffee.
Coffee is black.
Charcoal.
Charcoal is also it's a compound. I'm asking about the element. What element do you need?
Burn wood.
Burn wood is also an element.
Carbon.
Correct. So carbon is needed for creating the black. Correct. So you know that the carbon is there from everything, from a very small pencil to everything around us. Even we are made up of a little amount of carbon. So everything is around us is made up of carbon in some form or other. So carbon is 6 parts of proton, 6 parts of neutron, and 6 parts of electron. So can you see how many electrons are moving around that center of that atom? How many are there?
6.
2 in the first circle and 4 in the second circle. So 2 plus 4 is 6. So like this, every small circle is an atom. So like this, every small circle is an atom. So like that, if you keep on adding and adding and adding, it becomes a very big carbon atom. So why do we need to know this? Because fundamentally, if you start to break an atom from a very small atom, if you start breaking it, it becomes a very small center called a nucleus. From nucleus, if you break that, you can create protons and neutrons. Even if you break protons, there becomes even smaller things called quarks. And from quarks, we don't know what is going to happen next. So they are very small. They are so small, so tiny that you can't even imagine how small it is. It is 10 to the power minus 18. It's atto scale of measuring elements. So there is I'll try to remember it. I don't know if I'm perfectly right. It's tera, giga, mega, kilo, hecto, deca, deci, milli, micro, nano, pico, femto, atto. So that is 10 to the power minus 18. So this is the smallest of the smallest size that you can go. So if you start to find, there are about 12 different types of elements, and these 12 elements are, sorry, 16 elements that are there in the standard elementary model. And these neutrons, these very small neutrons, can be broken down into quarks. Can we see a quark in a microscope? Not even a powerful electron microscope can see a quark. So quark is very small. So it is to the scale of 10 to the power minus 18 and even below that. So nobody has yet to understand it, but there is a theoretical model. There is a theoretical calculation that creates that has to be some kind of elementary particles that is beyond the nature of smaller neutrons. Is Proxima Centauri and Alpha Centauri are sun-like stars? Proxima Centauri, I'm not sure it is exactly like a sun-like star. I think it is, one of them is a middle-aged star. I'm not sure which one is. Either Alpha Centauri has to be a middle-aged star, but Proxima Centauri is it's a dwarf type star. It is a little older star. It is much older than us. So not like our sun. It is much older sun. So coming back to it. So this things that we see as an elementary particle is the most smallest thing that you can see. From big atom, even the big atom, you can break it down into a very small nucleus. From nucleus it goes to proton, from proton it goes to quark, and from quark it is very small. And if you try to break a electrons, we don't know what it becomes. So it has been hypothesized that hypothetical is, people are trying to find the reason what will be the smallest thing that you can go into. So this is what we are studying. And as I told you, we are in the smaller star range. So we ourselves, from a sun's perspective, we are a very small star. So we can become a red giant, and we can become a nebula, and probably we can become a white dwarf. But what happens to a very massive star? So it can become a neutron or a black hole. So how big of us can we become? So we are very fortunate because we are in the range of a white dwarf. It is a very normal star, very normal looking star will become a white dwarf. Or probably if something like Betelgeuse or Rigel, all these things will become a massive neutron star. But what about things that are even farther and bigger and bigger? All the center things that it can become a neutron star at a very faster rate. So this is what we are going to be looking at. So this small things, that the very tiniest of the tiniest star, that is a neutron star, it is the ones that we are always interested about to know, because they are constantly giving out lot of light. This light is a very pulsating light, kind of like that. It will constantly come towards us. This is a blinking light, like a blinking LED light from your night lamp. So all these things are doing very mischievous things in our sky. So when you compare it, all these things, the most smallest of the smallest stars, even a quark star has been discovered, and they are very so small, very tiny, so tiny that if you compare it, these tiny stars are something like a size of a Burj Khalifa tower. You know what is Burj Khalifa? You know where is Burj Khalifa?
Sir, I know it because I built a Lego Burj Khalifa.
Oh, very good, super. So where is Burj Khalifa?
In Dubai?
Ah, very good. It's in Dubai. So it's the tallest building in the world. And if you make it, all the iron and steel inside that Burj Khalifa will fit into one small tiny box.
I
That,
have that to Burj Khalifa
how?
because I'm in Dubai.
Oh, okay. So okay, super. So when you look outside, all the Burj Khalifa's iron and steel is there, right? So it's a very tall tower. So when you compress it and you put it into a very small box, this small box becomes the actual measure of a neutron star. And when you compare it, it will be even bigger than that of all surface area of the Mount Everest. So it's like 1 billion square meters all compressed into one small cube. So that is how dense it is. So this is a very famous place in Chennai. What is this?
Marina Beach.
So this is Marina Beach. So if you take all the sand from Marina Beach and you make it into a round ball, round white color ball, what will it become? So it is around 10 kilometers. It's around 10 to 12 kilometers. So all the 10 kilometers sand, you take it and you put it into
It
one
will
round.
become smaller than before.
It'll become almost to the size of a one neutron star. That is how the size of a neutron star is.
It's too small.
Yeah, that's all. That's the size of entire neutron star. So this is something that is scientists are unable to understand. So it is a very dense thing, but it can able to bend light like crazy. So it can bend light like a very crazy thing. So it can absorb light, it can bend light, and it can make a lot of interesting things. So I told you before, scientists have been trying to understand the nature of space-time. That is, why does time have to bend around things when they are having a very larger mass, say like our sun. Time bends around our sun in such a way that we have a kind of a fabric that is floating around in space. And even neutron star also does the same thing. The first time this was observed was in the year 1990, where this is a very famous scientist. You know what his name is? Any guess?
Yes, sir. 1 minute.
He is always having a tongue out like that.
Yes, sir. I know, but I forgot.
He is Albert Einstein. So Albert Einstein was the first person to have devised a method to find the bending of light. He had a very ingenious method. You know what he did? He sent two batch of scientists. So one batch went to South America near a place called Brazil, Sobral, Brazil, and one person went to close to Jamaica. There is an island of Príncipe. So island of Príncipe and Brazil are in the opposite sides of the Atlantic Ocean. So both sides they started observing the solar eclipse. That was in 1919. The year is 1980. So almost 102 years back. So imagine there was no much bigger technology. So 102 years back, he sent two batch of scientists to observe the solar eclipse that was happening at that same time. What he found out was the light that is coming from a different star and that is behind the sun is slightly bending by the nature of the solar eclipse. So through that, they were able to find that every time the light that you see is taking a large distance to cover. So whenever there is a heavier object that is in front of our view, the field of view, it is bending the space-time. So like that, they were able to find lots of reasons to undergo theoretical physics, and through that only general theory of relativity was evolved. So E equals mc squared is a derivation of all these things. So what happens next? Have you seen this kind of sports? What is the sport called?
Ice skating.
Ballet.
Ballet is also there. Ballet is also a form of ice skating, but it is called ice skating. What is the thing that I'm trying to tell you here? What is happening?
The angles of the turning.
No, for first image, she is having her arms stretched out, right? Her arms are stretched out, and when she brings it closer, what happens?
She's rotating differently like before.
Rotating differently, rotating faster, slower. What is the difference?
Rotating faster.
She's rotating faster. You know why? What did I tell you before? What did I mean by this? All this sand in the same space. What does it mean by sand in the same space? It becomes a white color sand, densely packed. What does it density means? Anything can be right. Any answer is right. There is no problem. Nobody is going to give you a mark or anything. If you ask questions, you can get a lot of answers.
Sir, can you say the question again?
What is happening here? What is the reason for her to spinning faster? What is the reason for her to spin faster?
Because of the air around her.
Okay, almost right.
Because of the distance covered by her is bigger in before, and
Okay, but Litika, what did you say? What did you say?
Because the floor is smoother.
Floor is smoother. Okay, but that's
Friction is less.
okay. That is also there, Kanama. But what happens when she's putting her hands very
And
close?
because when it's outside, she's like keeping her hands in the air, so the air around her is not spreading properly.
Uh-huh.
But when she keeps it inside, the air is spreading properly and it's making her go fast.
Okay, so that's also right. So that is called density. So when you are very dense, when you are very tightly packed, it becomes easy for the air to flow around you much faster. So like that, even the neutron star is gaining a lot of speed when it is very very dense. So as the figure skater or the ice skater is moving around in space faster, the spin rate of a neutron star is very very fast because it is very dense. It is so circular, it is so dense, it is combining all the sands of the marina beach, so it is like very close to each other. So it is spinning so fast that it is sucking everything across its space. So if a sun like star comes very close to a neutron star, it will suck everything like a noodles. So it will start sucking it and it will become a very massive cloud of dust. So this spin rate is very fast. So it is like 700 times per second. That is a normal rate. But the topmost layer, that is the one with all this carbon, helium, and hydrogen, all these things, it is even spinning much faster. So this is called an accretion disk, and this results in creating different types of neutron stars. So when they are very far away, when the ones that I showed you, the ones that do not have any reason to move around in space, like this one, it will always stay quiet and it will never move around. So that is a silent type neutron star. The next one is a binary pair, pulsars and magnetars. We are going to see one by one. So this is a binary pair. So one is a neutron star and one is a middle-aged normal looking star. So they both combine together to become a binary pair. Next is pulsar, the ones with so much amount of magnetic radiation that it is pushing out in every direction. So there is a huge magnetic flux. What is this? All this circular, round things across this.
It's the magnetic radiation.
It's a magnetic radiation. It's a very powerful radiation. If a very small amount of magnetic radiation hits you, it can destroy all your DNA, your chemical makeup and everything, and it can tear you apart. So like that, it is constantly pushing this light across this galaxy. So anything that comes in the path of a pulsar will die immediately. And this is very highly magnetic, and it is very very fast, and it is more than 20% faster than the speed of light. So it is faster than the speed of light, yet still it is quick, it is much quick. So scientists are trying to observe this phenomenon, that is the fast spinning rate of a pulsar, using telescopes which can completely block a view or create a new pulse, right, and it can suddenly go dark. So this kind of very quick succession is used for measuring a lot of things. So scientists are trying to find a space clock using a pulsar. So the next one is the remnants of a pulsar with a nebula. So it's a crab nebula, and inside it is a very fast spinning pulsar which is exactly in the middle. So this is the shock front of a pulsar. It's a very very small thing. So next one is magnetars. Magnetars are even much bigger than them, and they will also try to stay a longer period of time. They will stay for at least 10,000 years, and after that they will start to slowly decay. But they, instead of creating very strong magnetic fields, they will give sudden burst of energy that is coming in the field of X-rays and gamma rays. So what will happen if two magnetars combine together? It becomes a very very bright light. So it can create a different kind of nebula if a magnetars combine, or a neutron stars and a magnetar combine together to form a very large type of explosion. So this brings us to the end of this week's session, and we found about what are the different types of particles, what is the density of a neutron star, and what are the types of a neutron star. So we also have a very good news. We are going to know more about our Mars explorer. What is this Mars explorer called? Can anyone tell me?
Perseverance rover.
Perseverance rover.
Perseverance.
Yes, Perseverance. Perseverance did something very remarkable last week. It had sent the first
20
success.
months?
It has sent first successful test of spinning of the blades of the small guy, the little guy called Ingenuity, that Kuti Kuti rover. So it has started spinning. So they are doing testing today. Probably tomorrow morning or day after tomorrow, they are going to try to fly it. So this is the good news. Nitin is going to see a flying helicopter the first time in Mars. So this is happening tomorrow, and this was successfully done after a kind of test that they did. It's called a watchdog maneuver that is supposed to have when the mothership is looking at a baby. So constantly it is monitoring it. So it is checking whether it is going to successfully fly or not. So because the Martian weather is very bad. So Mars, almost 365 days, there is always bad weather. So there will be so much of heat, there will be so much of dust storm, there will be so much of clouds covering all the light, sunlight, all these things are happening. So probably by tomorrow, this time we will be seeing Ingenuity making its first flight. So this is going to be the test area. So they have planned a test from this space that is around uh, 2 to 3 kilometers range. So they have planned, and they are going to try to find a way to measure it, how it is going to fly in that area. So it is going to make small incremental jumps. So from it's going to fly for about 12 feet, hover there for some time, and then drop down again. It's going to hover for some time, drop down again. It's going to do this multiple amount of times over a period of many attempts. So for the next 2 weeks, they are going to fly it and see how it performs. So this is it for today, and we are going to see about what is an art cloud. That is going to be the next week's episode. So, mm, so what do you have as a question? What questions do you have?
So,
Yes.
so why can we see auroras only in Netherlands?
Good question. The reason is um, most of our atmosphere is filled with thick amount of cover. That is layers and layers of magnetic field. But it is very thin in the north and the south pole. The north and the south pole is filled with so much amount of free flowing electrons and free flowing atoms because of this thin layer. Because of this, whenever the north pole and south pole is in contact with radiation from our sun, it absorbs all the magnetic radiation. Because of this, it creates a kind of colorful aurora. You can
So,
also,
what's the aurora made up of?
auroras are made up of charged electrons. So most of them are free flowing nitrogen atoms. About 70% nitrogen atoms. Sometimes it will also create another color. It will be in pink color, it will be in pale blue, depending on the composition of the gases that is there in the north pole. Even in south pole also you can see aurora, but south pole is not very favorable for us to stay because there is no perfect climate in Antarctica. You know why?
It's too cold.
It's too cold. Yes, true. And there are longer summers in Antarctica than in Arctic. Summers in Antarctica will last for about 7 months, 7 to 7.5 months. So there'll be 7 months of daylight. So if you go outside now, it will be dark, right? You are in India, you are in Dubai. So by the time you go outside, it will be starting to get dark. Okay. But if you go now in Antarctica, it will be looking like 3 o'clock in the afternoon. It will be so bright. Even at the midnight, 12 o'clock, it will be very bright. You will be bored. Cha, no time to sleep. Always sunlight. Like that will be there. That is the problem.
So,
So
the ultraviolet rays are so hot.
ultraviolet says if you stay a little longer than maybe couple of minutes, it is very dangerous. It can
It can lead to skin cancer.
It can lead to skin cancer. Before that, it will open up pores. There is something called melanin. There is a pigment called melanin in top of our skin that is protecting us from the harmful radiation.
And the ozone is also.
Ozone is also there, which is also protecting all our harmful radiation. So if we create any holes in the ozone layer, this ultraviolet will directly fall to our skin and it will break open the melanin pigment, and all it will go inside and it will kill the cells inside our skin. So this dead skin cell is called a skin cancer. A cancer is nothing but it's a dead cell. It's a margaya cell. It all died.
Will it ever be hot in Saturn, Jupiter?
Will it ever be hot? Um, no, I don't think so. They will always be very cold giants for for the next foreseeable future. I don't think they will ever get hot. They're hot. They can become hot depending on the things that are given into it. So if you send a spacecraft, because of friction, they will get hot and they will get burned up. Apart from it, it will always going to stay cold, and they're going to be floating there for a very long time. Their surface temperatures will not go beyond minus 200 or minus 300 degrees.
So, what's the difference between planetary nebulae and nebulae?
Planetary nebula is just a name. It doesn't have to be a kind of a term that is given. See, when scientists try to look at look at things through the telescope, they don't have an actual understanding of what they are looking at. So what they'll do, they'll ask people, they are the scientific community people, to give them a valid name for it. Okay, uh, you are looking at your friend after say 3-4 years. Okay, okay, you imagine that you are time traveling and you are looking at your friend after 15-20 years. Suddenly you find that all that she is now, she's having 6 feet of hair. She has started wearing dupatta and she has started sari. You don't even recognize her, right? So what will you call her? Will you call her as a friend, or hey, hi machi, hi friend? Will you call her like that, or will you call her like madam, how are you madam, like that? What will you call her?
Hi, madam.
Hi madam, because you don't know if she knows you, correct? Like that, every other planetary body is not known to us. So whatever we try to meet some new planetary body, we will give them a very respectable name. We will call them like planetary nebula. We will call them with a number C1452b. All these kind of numbers, we will give them a respectable number. And after that time, when they find another reason, no, it is not a planetary nebula, it is normal nebula only, so it has taken a little longer time. All these things we have to understand over a period of time.
Sir, I have a telescope.
Very good, super. What have you found using the telescope?
I just saw the moon.
What is the magnification of that telescope?
No,
You have to go and see what is the small f. There is this thing called small f written next to it. That is called the focal length. Okay, that is next to it. There will be giving a three number of sets. Magnification lens in 25 mm, 100 mm. There are also other compounded lenses, so you can check what is the magnification factor of that particular telescope. So that will be useful for you to find different objects. You can, if you can comfortably look at moon, I think it is very easy for you to spot Saturn. I think Saturn, yeah, Saturn can be found around 7 to 8 p.m. in the night. You can find Saturn in a very clear sky.
yes, sir. One day I'll try.
Because summer months are very quick to find a lot of stars. A lot of stars and a lot of planets you can find in the summer months. You can also download and install that Sky AR app, so that you can point your phone on your sky and see which direction the star or the planet is going to come. I'll send you the link, so it will be easy for you.
Okay, sir.
Ritika, very quiet today. Yeah, no, you're very bored. Don't like Nebula. Don't like Neutron.
I think I asked lots of questions.
Okay, no problem. You can ask questions. Ritika,
So
so
many people left the class.
so many people have left because Kanama, they are all finding it very hard to learn. One of few children thought that I am talking so much of science and they are getting bored. They think that Abhi sir is like so much of science fellow. Now he stopped talking astronomy, is taking science classes. You like science, Ritika?
Yes, I like science.
So that's why you're staying. All the other people don't like science. They like other things.
Sir, I love science.
See, people who love science can understand me. That's the reason. Or you have any friends who would like to understand more about astronomy and science, Ritika?
No, ma'am. No,
No,
sir.
no problem.
Only I have like all of them like maths. I hate maths.
I hate Max. Ayyo. It's not like you can't hate Max. Max is going to follow you all through your life. What is 1 plus 1?
Two.
Like that, it is going to follow you all the time. So, what other questions you have, Samita?
That sounds.
So, we'll finish this session.
Yes, sir.
Bye bye. We'll see you next week. I'll try to bring Madam Divya next week. Okay, for sure. Okay. Bye bye.
Bye, sir.